as promised on this page, now we're going to take a break from the solving and practice that simplifying. And basically, when I'm simplifying square roots, I'm just trying to see if there's any perfect square factors that go into that number in the square root, which is called the radicand. So my perfect squares I'm looking for, we have a chart in the first lesson if you wanted to look back there, but they are basically 1, for some reason this is not writing, sorry, 1, 4, so this is 1 squared, 2 squared, 3 squared is 9, 16, 25, 36, and so on. So if you went back to the second page of your lesson, or the second page of your packet, there's actually a list of those. So it's the same, we're using them differently, but it's those same perfect squares from difference of perfect squares. So when I look at 20, I know that 20 is 4 times 5. Now, 20 is also 2 times 10, but 2 and 10 are not on my perfect square list, so I would never use them in this case to break it up. So basically, I just break up the square root into the square root of 4 times the square root of 5. The square root of 4 is 2. So this simplifies to 2 radical 5. Looking at the next one, 48 actually has 4 go into it, but 16 is the biggest perfect square that goes into 48. So the way I can tell that, and I don't write this down, when I write this, if I picked the 4, let's say I thought 4 was the best choice, that 12 still has another 4 in it, right? So the 12 is 4 times 3. So if I have extra perfect squares, like I have 2 of them here, I could have just written this and found the 16 first. Now this process of writing things 3 different times to get to what I really want is not really something you want to do. It's very error prone. So you always want to find that biggest perfect square first. So I'm going to start with that 16 and 3. So the square root of 16 is 4, square roots of 3. The next one, 27, and I would suggest just trying these. I know that when we get to the fractions, you'll have to watch a little bit. So 27 is 9 times 3. So that's 3 square roots of 3. In general, it's always best to write the perfect square first because then you can simplify the first part, such as the square root of 9, and leave the second part. The next one is maybe not so obvious. If you're stuck, just start trying different perfect squares, seeing if one goes in. You can also do that trick to factor numbers where we do y equals the number divided by x, so 98 divided by x. This one does have the next perfect square that goes into it, which is 49. So that's 7 radical 2. Now, when we get to letter E, 10 could be broken up into 5 and 2, right? But neither of those are perfect squares. So there actually are no other numbers. There's no way, 4 doesn't go into 10 evenly, right? So this one just stays. So that's already simplified and there's nothing I can do with square root of 10. Square root of 200 is 100, which is the perfect square times 2. So square root of 100 is 10 and then square roots of 2. So I mentioned that square roots are distributive over multiplication, which means that we can take a number and if we break it up into multiplication, I can put a square root on each one. It also works for division. So this problem is equal to the square root of 3 over the square root of 4. I can distribute that and then I can take the square roots individually. So the top just stays square root of 3 because 3 isn't a perfect square and it doesn't have any perfect squares that go into it. The square root of 4 we can simplify, and that's 2. So the next one, the numerator simplifies to 2, and the denominator has to stay. Now, in math, when we're simplifying, there is a rule about not having square roots and denominators, and the best I can tell the reason that is it makes it harder to create common denominators to add fractions together. Don't really have another reason, but basically that square root can't stay in the denominator, okay? So when we get in this case, this is the thing that's illegal, square root left in the denominator. What we do is something called rationalizing the denominator. So that involves whatever radical's down here, I just multiply by that radical times itself. Now in my numerator, multiply across, I have 2 radical 3. the square root of 3 times the square root of 3 is the square root of 9. We multiply those numbers in the radicals, and ultimately, this will always work. The square root of 9 is 3. So this property, this is an identity. Whenever I do the square root of a number, so I'll write this up here, square root of a number times the square root of a number, it always equals just that number. Basically, a square root times a square root or something times itself is squared, opposite of square root, they cancel, I just have the number left. So this is my final answer. We're going to use that on a couple more. So first thing we do is split it up. Neither of these simplify. I have a square root in the denominator, so I'm going to multiply by the square root of 3 over the square root of 3. This gives me the square root of 15 over 3, right? This becomes square root of 15, that becomes 3, and that is simplified. So square roots in the numerator are fine, square roots in the denominator, not so much. Looking at the next one, we have square root of 8 over square root of 7. The numerator does simplify because 8 breaks up into 4 times 2. And then this numerator becomes 2, radical 2, over square root of 7. I have to rationalize the denominator, right, because I have a square root of 7 on the bottom. So multiplying here, in my numerator, my numerical 2, or my constant 2, my regular 2 stays. My square roots get multiplied together. Radical 2 times radical 7 is radical 14. And in my denominator, square root times itself is just that number. So 2 square roots of 14 over 7 is my answer. Not pretty, but that's what it is. Now, you always have to be on the lookout for ways that we can make the problem easier to do. On this one, 81 divided by 3 is actually just 27. So I don't even have to think about the fraction. I can just get rid of it. And then from there, this is going to simplify. We actually did this up on letter C, right? 9 times 3. Square root of 9 is 3, so we get 3 radical 3. Letter L, I'm just going to move up the page a little bit. So letter L just brings in another situation, and it's not really new. We just have to kind of connect it with what we know. So here, that 5 is just on the outside. 60 breaks up into 4 times 15. So that 5 is staying on the outside. This becomes a 2. Now here there's multiplication, so here there's still multiplication. So it's 5 times 2, radical 15, and then we can multiply the numbers together and get 10, radical 15. So sometimes people like to throw an addition sign in there. There is none. That's how we would simplify that one. Okay, so moving down the page, now we're going to head back to those incomplete quadratics. We practiced some simplifying radicals. So here, I'm going to subtract 4. And once again, it's incomplete because there's no x term. And then multiply by 9/2. So this actually gives me x squared. This is cancels out. You can do that on a calculator as well. So this actually gives me x squared equals 81. From there, I can take a square root. Remember, 2 answers, so I get plus or minus 9 as my answers. Looking at the next one, I can subtract 5 and divide by 4. So now I'm going to take a square root. So here's my fraction situation. So I get x equals, don't forget your plus or minus, the square root of 3 over the square root of 4. We distribute that square root over division. So this is radical 3 over 2 for that one. There's no radical in the denominator, so I don't have to go further with that.